All right, here we go. Next lesson, cylinders and cones. We're really going through these shapes very quickly. All right, here's your homework. All right, cylinders and cones. You know the drill by now. I'm going to give you the shapes. We're going to do two formulas, one for surface area, the book likes to call that total area, and one for volume. Just quick reminder, we've been talking about polyhedrons, and polyhedrons are three-dimensional shapes where the sides are made up of all polygons. And as the picture right here presents, there's lots of polyhedrons in this picture, but there's some of these that aren't completely made up of polygons. In fact, the cone, the bottom's a circle, so that's not a polygon. How about the cylinder? That's not a polyhedron. And lastly, the sphere. I can't draw a circle, apparently. The sphere doesn't have any polygons whatsoever. So today we're going to do the cylinder and the cone, and then the only thing we have left is the sphere after that. So that's kind of what we're doing today. All right. So we'll do the cone and the cylinder today, and we'll finish up the chapter with the sphere. So the last few classes, we've been dealing with polyhedrons. We get a formula for surface area, or total area as they like to call it, and one for volume. Now, they like to take the total area and break it down into the base area and the lateral area. And so the lateral area is just the side. And in fact, our book usually doesn't even give us a formula for total area, but it asks us to calculate that, strangely enough. And so I will give you both formulas. All right. We also talked about surface area as a net. And if you can take any shape and break it down to just its surface and lay that surface flat, there's a rectangular pyramid right here, and there's the net of it there to the right. And that's one way to at least geometrically or visually think about what we're actually doing when we calculate surface area or total area. So different day, but the same drill. All right, total area, we'll break that into lateral area plus the base area, and we'll do volume as well too, but we will do it for cylinders and cones. So remember, in 3 dimensions, if we need to draw a circle, if you actually draw a circle, because remember we're drawing in 2 dimensions, you draw a circle, these shapes don't look right. So when you draw we'll do the first shape, we'll do a cylinder. When you draw the cylinder, yes, technically I am drawing a circle, but I'm going to draw an ellipse there. And then directly above that ellipse, I'm going to draw another ellipse. But remember, in reality, I'm drawing 2 circles. Connect the sides, like go all the way around the sides. In other words, the circumference of one of those circles. Let's see, the distance between the 2 circles would be the height. And if we were to connect that with a rectangle in such a manner, put those 2 shapes together, we would in fact get the cylinder. Now, the key point and the reason why I was showing you this is the fact that this rectangle right here, where does it come from? Well, where does it come from? It's the curved surface that joins the 2, well, I'm going to tell you the word here in a second, the 2 bases. But that curved surface, if you lay it flat, is that rectangle right there. Well, a rectangle has dimensions of base and a height, but the base here, because that has to go all the way around the circle, the base would actually be the circumference of either one of the 2 bases. And so therefore we can calculate the lateral area fairly simple. So let's start off and let's write some of this stuff down. So we'll start off with the basic definition of a cylinder. So a cylinder is 3D, obviously. It's not a polyhedron because it's not made up of just polygons. So it has 2 congruent circular bases, and then that curved surface. So I'm going to go back to the picture for a second. That curved surface that joins the 2 circles. So a 3D object with 2 congruent circular bases and a curved surface that joins them. That's the definition. All right, and as always, now we talk about the parts, and you could probably already guess what the parts are going to be. We'll start off with the 2 circles. Those are called the bases. And just so you understand, those 2 bases are congruent circles. Well, what would happen if one was smaller than the other? Then technically what you're making is part of a cone. And we'll talk about that one next. But the two circles of a cylinder, and it's like a can of soup, right? The two circles have to be the same size. Oh, and lastly, those two shapes are also, the two circles are also parallel to each other. So top and bottom are parallel. So we'll talk about the side, that rectangle that joins the two circles. That would be called the lateral area. Some books call it the lateral surface. Lateral area is fine. What's left? Let's see. Oh, the distance between the two circles, right? That was what we're going to call the height. So remember, that's measured perpendicularly. So the perpendicular distance between the two bases, that would be termed the height, h for height. And let's see, any other parts? No, cylinders are pretty easy. There's not too many parts to them. Now, usually now we talk about the types of cylinders that exist, and it's always the same. Once you learn this in three-dimensional objects, you'll see that similar pattern. So let's see, if the height and the radius form a right angle, it could be the diameter as well too, then we call that a right cylinder. So if the height and the radius, or the height goes through the center of the circle, one of the bases, and forms a right angle with that base, then we call it a right cylinder. And then the second type, if you could imagine the top base there pushed sideways, left or right, well, now that right angle wouldn't be a right angle anymore. I push that top circle to the right, I get a slanted cylinder, except we don't call it slanted. We call it oblique, because remember, the height now wouldn't go through the center. Oh, so where would be the height? Well, this is one of those ones where we'd have to offset the height. So let's see. It can be drawn a couple different ways, but a lot of times they'll just draw it with a dashed line like this to the center right here. And they'll simply say, this is the height right here. Okay, now we're not going to do oblique triangles, or I'm sorry, oblique cylinders in this lesson. We're just going to do right cylinders. So think about this. The net, remember, that's if you could imagine just the surface of this shape, the cylinder, and if you could pull it away from the shape and lay it out flat, well, let's see, we would have two circles, top and bottom, and then the curved surface, if you laid it flat, it would make that rectangle right here. We're gonna derive the formula for total area here. So let's see. Well, I know two circles would be pi r squared, and there's two of them. I know that rectangle, the height of the cylinder would be the height of that rectangle, and the base, let's see, the base would be the circumference. And so the lateral area, if we want the formula for the lateral area, that's this red square right here, red rectangle, sorry. So the lateral area would be base times height, but the base is the circumference of either one of the two bases. So it'd be circumference times height. So instead of saying BH, because it's a rectangle, the base is the circumference of a circle, and the circumference of a circle is either pi d or 2 pi r. So I can write B as 2 pi r times the h, and we get to our formula for lateral area. Lateral area of a cylinder is 2 pi r h. So there's our first theorem. Given a right cylinder, that the lateral area, or that curved surface right there, which if laid flat, it's a rectangle, would be 2 pi r h. So the lateral area of a cylinder equals the circumference of its base, that's 2 pi r, times the height of the cylinder. All right. Once again, our book doesn't give us a formula for total area, but we can figure this out. So if the lateral area is 2 pi r h, that's the blue portion, well, the cylinders would just simply add two more circles, and those circles are called the base. So it would be the lateral area plus, well, not one base, but two bases, right? And the base is equal to pi r squared, so 2 pi r squared, because there's two circles. So put that together with our lateral area, which is 2 pi r h, and we get our final formula for total area, 2 pi r h plus 2 pi r squared. No, we don't get this for a theorem, so you're just simply going to need to add this to your book of truth. So total area of a cylinder is 2 pi r h plus 2 pi r squared. All right. this is not a theorem, meaning that I'm going to prove the formula, but I'm using the fact that we know the area of a circle is pi r squared. But remember, I never really proved that to you. I simply gave you some solid evidence. Remember, we're doing that table, and we figured out the area of a circle is pi r squared. We didn't rigorously prove it, but we found some very strong evidence for it. All right, so total area of a cylinder is 2 pi r h plus 2 pi r squared. That's the same slide as the previous one. I just wanted it as a separate one. And I also wanted to make a point here that I didn't truly prove this. I did prove where the formula would come from, but I'm using the fact that, well, circumference is 2 pi r and the area is pi r squared, which I've never proven. All right, quick side note. The question, you've seen this before. The question will say, leave your answer in terms of pi. So when the instructions state leave your answer in terms of pi, that means do not multiply by 3.14 or use the pi key on your calculator. Just use the symbol or leave the symbol pi as pi. So you do not multiply by pi in the formula. So 2 pi r would simply just be 2 times whatever the radius is. So for instance, if the radius was 3, 2 times 3 is 6, you'd write 6 pi, and now your answer is in terms of pi, 6 pi. All right, so let's do one. Total area of the cylinder. Well, let's see. The formula is 2 pi r h plus 2 pi r squared. So I need the radius and the height. Please, hopefully they gave us this. And look, joy, they gave us both the radius and they gave us the height. Remember, for a right cylinder, the height is the perpendicular distance between the two circles or the two bases. How could they mess with you? Well, they could give you the diameter. You'd have to cut that in half. I guess they also could, let's see, they could make this into a triangle right here and give me that value of that blue line. And then maybe if they were sneaky or something, erase this 4. But they would have to give you this value right here. Now, if they gave you that value in one of the sides, we could use Pythagorean theorem to find the other side. So I guess they could do that as well too. But here they're very nice to us. They gave us everything that we need, the radius and the height. So this is just a plug and chug formula. We plug the numbers in. Now the instructions there do say leave in terms of pi. So we're not going to multiply by pi. So let's see, going from left to right, I want to multiply the 2 times the 5 times the 4. 10 times 4 is 40. Leave pi as pi, so that'd be 40 pi. And then we got to do 5 squared first. That's 25. And 25 times 2 is 50. So I would get 40 pi plus 50 pi, which is 90 pi. And are we doing volume or are we doing area? We're doing area. So 40 pi plus 55 is 90 pi. Units are centimeters, so centimeters squared. That makes sense? Okay. Once again, as always, we're going to do one for total area and one for volume. So let's see if we can figure out the formula for volume of a cylinder. So there's a cylinder. I'm going to claim that one's right. You take a right cylinder, and if you think about this as a bunch of thinly sliced circles, I mean really thinly sliced circles, well, then the shape you're making are circles on top of circles. And we can calculate the area of any one of those circles. So how many of those circles do we have? Well, that would be equal to the height. And that's where we're going to get our formula from. So for right cylinders, the formula for volume is, well, it's one area of a circle, say the bottom one. So that would be pi r squared, because that's the area of a circle, times the height. All right, so that's volume of a cylinder. So once again, just like in total area, this formula only requires us to find the radius and the height in order to do this calculation. Not too bad at all. Same problem before. Look, they gave us the radius, they gave us the height. So I just need to toss those values in for r and h, and the question states to leave it in terms of pi. So I'm not going to multiply by pi. So let's see, 5 squared is 25, and 25 times 4 is 100. The pi is still there. So we get 100 pi, the units are centimeters, and since we're doing volume, then it would be cubic centimeters. Now, I guess I've never really answered the question, why do we leave things in terms of pi? Well, if you leave the answer in terms of pi, then you get to use an equal symbol. But pi is an irrational number. Yes, it's approximately 3.14, but it isn't 3.14. It's 3.15 and a bunch of other decimal places that continue, and they never stop and they never repeat themselves. So no matter what actual number I use for pi, if I use an actual number for pi, I'm doing some rounding. So if you do not say leave your answer in terms of pi, then your equal signs, for instance, if I use 3.14, now becomes an approximation. Why are you not drawing? Becomes an approximation symbol. So yes, you can, if it says rounded, there's 10th or 100th. Yes, go for it, use 3.14 and then round. But mathematicians would love you to leave it as the exact answer. And the exact answer is 100 pi cubic centimeters. As soon as I change that pi to 3.14, then it's approximately 300, and let's move a decimal place twice, 31.4 cubic centimeters. All right. Well, I said 31.4. I meant 314. I'm multiplying by 100. What am I thinking? Okay. My spidey sense went off there for a second there. We good with the total area and volume for the cylinder? All right, let's move to our last shape, and that is of cones. So there's a cone right there. Now you can see I've already sort of almost making the net of a cone here. I'm showing you how we could break it apart there. So we'll start off with the definition. I'll also tell you how to draw this one. So a cone is a 3D object, not a polyhedron, but a 3D object with a circular base and a curved surface that curves to a point. So we get a vertex on this. How do you draw a cone? Well, once again, don't draw a circle, but draw a squashed circle. That's pretty bad, but you get the idea. Put a dot directly above it and play connect the corners of your ellipse. And then since we couldn't see the thing in the back, we would have to erase. This isn't going to let me erase portions of. I can't make it dotted or dashed in this particular program, but there's a perfect one written or illustrated right to the left of that. So that's a cone. All right, let's talk about the pieces parts of a cone. As always, it seems like the first one is the base, and this one has one of them, and that base will be a circle. A circle. When you draw it in 2 dimensions, you draw an ellipse, draw it squished, but it is in fact a circle. Well, let's see. The sides of it is curved surface, so we would call it a lateral area or lateral surface. That's the side of the cone. We'll talk about what shape it is when we unravel it here in a second. Well, is there any other part to a cone? That looks to be about it, but there's a couple letters there. So the perpendicular distance between the base and the vertex of a cone is going to be called the height. And lastly, we have our friend L. And if you can remember from the pyramid, L stood for slant height. So cones will also have a slant height. So that's measured from an edge of the circle to the vertex, and it's measured once again perpendicularly. Notice I don't have that labeled there with a little right angle, but it's measured perpendicularly. All right, so those are the pieces parts. You can guess what the next slide's going to be. What kind of cones do we have? Well, if the center of, or if the vertex is directly over the center of the circle, that means that the height would form a right angle with the base. Then it's called a right cone. And if the vertex is not over the center of the circle of the cone, then it's called an oblique cone. All right, so those are the 2 types of cones. I guess all we have left are the total area formulas and the volume formulas. These are challenging. I cannot necessarily prove these to you beyond a shadow of a doubt, only because I'm going to be using ideas that come from area of a circle and circumference, but I'll do my best. All right. Oh, I'm sorry. I didn't show you that height does not go from the center of the base to the vertex. All right, so let's look about those formulas. So once I'm going back to this shape right here, it kind of gives you a, I don't know, foreshadowing of where this is going. So if I think about that net right there, if I open that up and lay it flat, it would look something like this. So let's see. They're giving you the impression here that there's actually two circles here. I don't know what the color that is, yellowish, and a blue circle right there. And the blue circle is not the entire circle. It's part of a circle. Also, using a term from last chapter, we'll call it the sector of the entire circle. Now, the blue circle and the yellow circle have different radii. The yellow circle has a radius of r, and the blue circle, it says L. Is it really the slant height? Sure, look at the original cone, and you can imagine if you laid that cone flat, that portion right there would in fact be the slant height. All right, so what are we going to do for the formula? So we'll do it one piece at a time. We typically do the lateral area first. So the lateral area would be this blue portion. And you notice it's not a full circle. It's only part of a circle. It's a sector. So it would make sense to use the sector formula from last chapter. So there's the sector formula, but we got a problem. Because remember, x was the central angle, and there's no possible way I can tell you what the angle is if this formula is supposed to apply to any cone. The second half of that formula there for sector is multiplied by pi r squared, and we can see on the blue circle that the radius is the L, or the slant height. So we know it's x over 360 times pi L squared. It's just that we don't know what the angle is, nor could we know if it's a generic cone. So we need to try to do this a different way. So here's the idea of what they do. Well, if you remember from the class, this portion was a percent of the entire circle, and this sector right here is a percent of the entire circle. In fact, it's the same percent. So if we think this in terms of not central angle, but instead of thinking this in terms of this arc right here, this arc compared to the entire arc, I'll do that dotted, that the solid arc compared to the dashed one would be the same percent as what this angle relationship would be. So I have another way of getting that fraction. Remember, that fraction is just going to be a percent, the one that I just circled. I'm just going to choose to use it in terms of circumference, and circumference of the entire circle would be the bottom, and then the top of that fraction would be the solid red line, and that solid red line would be an arc length. And luckily for us, we have formulas for both of those concepts. Well, the arc length of ABC, that's a major arc, over the circumference, we got a formula for both of those. If you remember right, arc length, well, the arc length, look at what that, if you can wrap that blue circle, I'm going to draw this for you. If you can wrap this portion right here back to this portion right here, then that would be the circumference of the little circle. So this portion right here, which is the arc length of ABC, is actually the circumference of the little circle. And that radius is, well, it's literally r, so it's 2 pi r. Now, the circumference of the big circle, well, I just need to know what the radius is, and the radius is L, so that would be 2 pi L. And you're like, okay, I understand that, but why did we do that? Because now we can do some canceling. Look at the fraction times the other expression that I just wrote, or other term. I've got 2 pi r over 2 pi L. Well, the 2's would cancel, the pi's would cancel, and lastly, I've got an L in the denominator, and well, pi L squared would actually be in the numerator, so I can cancel one of the L's off the bottom and one of the L's off of the L squared. So the only thing I would be left with is R, a pi, and an L. I'll just choose to write them a little bit differently. I'm going to write it as pi R L. And so all that work was just simply to show you or derive what the formula for lateral area is. And so the lateral area of a cone is pi r L, and that's theorem 12.7. All right. So the lateral area of a cone equals the product of the radius of the base times pi and the slant height of the cone. In other words, pi r L. As always, the book doesn't give us total area, but this one's a simple one. If the lateral area is pi r L and the base is a circle, then it would be pi r L plus 1 circle. And that circle, that's the B there, well, that's pi r squared. Put those two things together, and that is our formula for total area. I don't think I have another statement. Oh, yeah, I do. Here we go. Another theorem that's not a theorem. I didn't prove this one. It's not in the book. And the simple reason is because, once again, as always, I'll repeat myself, we've never proven rigorously that perimeter or circumference is pi RL or area of a circle is pi r squared. But if that were true, then the proof I just did for you was a rigorous proof. All right, let's do one. So let's see. It says calculate the surface area. That's total area of the cone. So there's my formula. Total area is surface area. Pi RL plus pi r squared. I need R and L, and I have R, 3. I don't have L. But looky with the height there, it makes a right triangle, so I can use Pythagorean theorem to find L. So I could throw those 3's everywhere I see an R, but to find L, well, then I need to do Pythagorean theorem. So let's see. One of the sides is 6, one of the sides is 3. 6 squared is 36, 3 squared is 9, 36 plus 9, 45. Take the square root of both sides. I believe 9 is in 45. 9 times 5 is 45. So the square root of 9 is 3. So 3 root 5. So that's my L. And I can see from the diagram my R is the value 3. So now we're going to throw those two values, R equals 3, L equals 3 root 5, into my formula and simplify. Now this one says leave it in terms of pi, so I'm going to leave pi alone. What can we simplify right here? Well, 9 can't be simplified, but 3 times 3 is also 9. But it's the pi and a root 5, and I can't join those two things together. A lot of people are going to want to add, because there's 2 9 pi's, and say, oh, look, it's 18 pi. Well, that would only be true if both terms had a square root of 5. This one does not have a square root of 5, so I can't actually add those together. So this is one of those examples where you get an answer, and it's very unsatisfying, and you're sure you must have this wrong, but in fact, you got this one right. I think the mathematicians will be angry with me. I think they'd probably want to put this in parentheses because otherwise it looks like the centimeter squared is only attached to the 9 pi. All right. So there is your total area. Can we do the volume? Well, we don't have the volume formula yet. So let's see if we can figure out the volume formula. Once again, this is not a proof. This is just a video of someone taking a cylinder with a given height and a given radius and a cone of exactly the same radius and exactly the same height, filling up the cone with liquid and pouring it into the, well, I'll let you watch the video.
Fill the cylinder if it is 1/3 of the volume. So let's fill the cone up the first time. And into the cylinder. Let's fill up our cone for a second time. And a third time.
Okay, so that is absolutely not proof. That is strong evidence that a cone is a third, because it took 3 cones to make 1 cylinder. So a cone is 1/3 of a cylinder who has, and if you can see there with the cone and the cylinder, they have the same base. So the circle is the same. I'll let it play for just a second longer when he puts it down.
To fill the cylinder.
And it has the same height. All right, so that's as far as we go. When you take calculus, you'll do a nice proof of it, but we can't do it in a high school geometry class. So there's our formula for volume. And this is a theorem. It's a pretty weak theorem because it's not really proven to you. It's just a video. It is what it is. The bottom formula there is typically what kids would use when they type it into a calculator. The book is the yellow one right there. So I always use pi r squared h divided by 3. The book always says 1/3 pi r squared h. Okay, we'll do one problem and that should be about it. Oh, wait, this is the same problem. Luckily for us, we just need the height and the radius, and we don't need to mess with the slant height. So the slant height we only mess with when we do it in terms of surface area or total area. So for homework, what they could probably do is instead of giving you this 6, right, erase that, and they'll give you a value for L. For instance, I don't know, maybe the side is 10. And then you would have to solve for your other side using Pythagorean theorem. So that wouldn't be too bad. But expect a little bit more work. I'm giving you one where it's just basically plug the values in. So radius is 3, the height is 6, toss those values in. 3 squared is 9. 9 times 6. Well, I guess I could divide 6 by 3 first. 6 divided by 3 is 2, so that'd be 9 times 2, or 18 pi cubic units. All right, as always, you get one of those tables for homework. They start off easy, then they erase one of the variables, and they give you the volume, or they give you the total area. You're a pro by this time of doing those tables. You know what to do. And yeah, here's a problem right here. It's a soup can and a label. Well, that would be the surface area, and the label would be the lateral area. Keep that in mind. There's an example of a table right there. So they'll ask you lateral area, total area. Remember, total area is lateral area plus base area. For a cone, that would be 1 circle. For a cylinder, that would be 2 circles. And V, of course, is volume. And that will do it for today. Hopefully you're having easy time through these volume and surface area problems. I would say calculation-wise, these are slightly more challenging than the 2-dimensional ones that we do. But I'll let you be the final judge on whether that's a true statement or a false statement. So I'll let you go here. Good luck with your homework. And if you have any questions, just ask away.